Okay, so first thing, I haven't had enough time to look at the exams to have a lot to say on them. I kind of briefly looked at them. They don't, the multiple choice kind of portion looks about where I think it would be. I'll start grading those probably this afternoon and tonight. I'm actually going to get the vaccine today, so hopefully I don't feel bad. But I will probably, I'm guessing I won't have them all done by the time we meet Friday. If I do, then I'll kind of have some more to say on Friday about it in terms of where the average was and things like that. But my guess is I won't have them all graded until after this weekend. So Monday we'll probably be kind of talking about where that mean up was. If it ends up being a little low, I might do a slight curve. But based off the multiple choice, I don't know if that'll be the case. Kind of depends until after I grade the short answer portion. So other than that, I'll put up a Learn Smart today as well as an online quiz after class. So the online quiz should be pretty easy. It'll be kind of related to what we talk about today. Then that Learn Smart will kind of get us ready for the next topic that we're gonna talk about, which is comparing two populations. Okay, so in other classes, sometimes maybe they'll refer to this as like, t-test. We'll see kind of what that means once we kind of work through all the material. But other than that, any questions from me before we get started here? Just kind of all the housekeeping stuff. Also, you'll see those third Excel assignments will start getting graded as well. I'm having my GAs kind of help me with those, so you might start seeing that grade pop up. And then once I have the second exams graded, I'll kind of reweight everything so that your best exam is weighted more than kind of the worst exam. And we'll talk a little bit more about that once we're at that point too. So like I said, my guess is probably not Friday, but probably on Monday we'll be at that point. Okay. So let's start. Oh, I can get the toolbar to get out of my way. There we go. So we're going to keep along the same line of hypothesis testing, but we're going to make it a little bit more difficult. So we're not adding anything new with the principles per se, right? In terms of how we find p-values, how we find critical values, all that's going to stay the same, okay? What we're going to start doing is kind of what we were doing when we were comparing confidence intervals. Remember we started to talk about we were comparing confidence intervals and if they overlap, right? We couldn't say anything, but if they don't overlap, we could say that one year was greater than the other or one group had a higher mean than the other. We're going to actually push that a little bit further. So we're going to start building confidence intervals, and we're going to do hypothesis testing for the same three situations that we used when we were only dealing with one population, right? Sample mean with a known population variance, sample mean with an unknown population variance, or all we had was a sample variance, and then proportion examples. So same three types of examples. It's just now we're going to be doing for two populations. Today, we'll kind of start out with the case where we know the population variances. We know this isn't the most likely case, but this is kind of where we start out, okay? And then finally, we'll get to this new idea, which we'll call matched pairs, right? So this is kind of a little bit different than maybe some things we've looked at before, but actually, once we get there, we'll see it's actually pretty easy, right? So almost feel like things get harder, and then once we get to here, it'll feel like things get a little easier. So the kind of examples that we're thinking about for these different types of confidence intervals and hypothesis testing, one might be, and we'll return to this, so don't feel like you got to write any of this down, but I'm just kind of showing them to you now. Maybe we've got two different types of majors. So I've got econ and theater majors here. I look at their starting salaries, based off of two samples I took, one sample of econ majors, one sample of theater majors, right? And I might want to say with 95% confidence, can I say that the econ majors make more, right, or less, or is there any difference? I might look at kind of survey responses and have a proportion where in 2011, 51% of people had unfavorable views of the Affordable Health Care Act. And then I took another sample in 2010 and found 48% of people. So 0.51 and 0.48 would be my proportions there from two different samples taken in 2 different years. Can I say that the views of the Affordable Health Care Act are actually different, right, between 2011 and 2010? And then I kind of have an example where we have drivers who are texting and not texting and their average response times, but I only have sample variances. Can I actually say that the response time of people who are texting while driving is any slower or is any different than those who are not? So those are kind of all of our three motivating examples. We'll focus on one today, which is comparing two population means when we know the population variances. So this was like motivating example. I guess I didn't put number one here. I put the numbers on the other, but number one. Okay? So if I have two populations, right, we can think of this as the econ majors and the theater majors. I took two samples. I think it was like 40 econ majors, 50 theater majors. I can find a sample mean from each one of those groups. But I know that each one of those sample means has its own distribution, right? So if I think about taking a sample from population one, there will be some true population mean, and there will be some true population variance. So we'll start kind of having to use subscripts here to identify this is the first population we're looking at, or this was our econ majors. So I've got my sample mean with sample size N1 from group one. I can then take a sample from group two. I know it has its own population mean, its own population variance. And once I take a sample, it may not be the same as the sample size I took from group one. Right? So I have a different sample size potentially, and I'm likely, if I'm looking at different groups, going to see different sample means as well. Okay? So now I've got basically two sample sizes and two sample means. Can I make, build a confidence interval? Can I do hypothesis testing? So what ends up being true, I'll kind of use the dot cam here to kind of show you that, and then we'll go back to that slide if you're worried about kind of writing that down. And I'll try to give the best visual of this as I can, okay? So let's say that we're thinking about the distribution of maybe our sample means, okay? Let's say I could somehow know what my econ population mean was for a second. So I'll use, instead of group one and two, I'll use E and T, right? Econ majors and theater majors, just to make this a little bit easier to think about. So maybe my econ majors are here. I usually pick on the theater majors, but here, the way I'm drawing this, they have a higher population mean starting salary, okay? May not be the most realistic, but it'd be great if it was. So each one of these groups has a different population mean, which means that the sample means we could see would be normally distributed around those true population means, right? So all I'm doing here is taking two groups and drawing out kind of their distribution of their sample means, okay? Well, what's going to be the most likely difference for me to see? So if I'm thinking about now the difference between econ and theater majors, right? And in terms of the levels, this won't make a lot of sense, but you can kind of see what's the most likely difference I can see. Well, the most likely mean I would see for my econ majors is here. The most likely difference for my theater majors is here. And so whatever that difference is, I could almost think about, I'm looking at the distribution of the difference in sample means, right? So I'm just thinking about here as my distribution of, and actually, sorry, this was what? Econ and theater, not one and two here. So the distribution of that difference between the two, well, the most likely difference I could see, here's the most likely outcomes. So this will be, if I subtract, the theater major mean from the econ major mean, whatever that difference is, that'll be the most likely outcome I would see. So, I don't know what that difference is, but I know that it's going to be whatever those true population means are. And then what's the next most likely? Well, looks like if I saw something here and kind of here on either side, so I start to get the differences on either side, or a little bit more likely. Well, what's the likelihood I see a really huge difference? Well, this is very unlikely. This would be very unlikely. And so it ends up being true. And there's kind of mathematical proofs out there. But as long as these are both normally distributed, and here's kind of the visual that try to give us the intuition, when I look at these two distributions of my sample means, if I'm looking at the difference between those sample means, the difference in the true population means will actually be where that distribution is centered around, and then will be normally distributed kind of to either side. So, we don't have to have like work through the mathematical proof of exactly why this holds, but this will hold. And kind of the intuition you can kind of see here, well, yeah, these will be the most likely values. So the most likely difference for me to see would be the difference between the population means. And then my distribution of that difference in sample means will be centered around that. Okay. Well, now I've got a normal distribution. Everything's going to be exactly what we were doing before, right? We've got, we'll take two samples, we'll find the difference. Where is that going to be? We could turn it into z-scores because we now know the mean of our distribution. So the only other thing we're going to need is the standard deviation. So if we think about the standard deviation for the difference in our sample means here, okay, it's basically going to be, it's probably easier to think about it this way. What would the variance be? Okay. The variance is simply going to be the sum of the variance from each group's distribution of their sample means. So we know that the variance on our sample means will be the original variance we sampled from divided by our sample size. And then we're just going to add that together for both groups. Now, if I wanted the standard deviation, all I have to do is take the square root. So it's pretty easy, right? We're looking at the difference in our sample means. They'll be centered around whatever the true population difference is, or population mean difference is. And this variance of the difference for our sample means will simply be the sum of the variance for each sample mean, right? Just adding those up. Okay. So if we want to write this in kind of more general form, not this E and T, right? The mean of my sample means, where that distribution is centered around, will be whatever that true difference is between the population means from group 1 and group 2. The standard deviation will be the square root of, if we're looking at the difference in our sample means here would be the variance of, sorry. All right, I'll re-say that since I didn't have switched over here in class. Okay, so I'm going to just repeat that. If we're thinking about the mean of the difference between our sample means, it's just centered around whatever the true population mean difference is. Right? The standard deviation would be the square root of our variance, and we said when I was writing that down that the variance, you just add up the variance of each sample mean. So the variance of each sample mean would be from group 1, the variance of the data you sampled from, divided by the sample size you took for group 1. For group 2, the variance of the data you sampled from group 2, divided by the sample size you took from group 2. Okay. So we're just combining those things that we already knew. Right? We knew that the distribution of group 2's sample mean would have this variance. Group 1's distribution of their sample means would have this variance. So to get the variance of the difference, we simply add those two together. Okay? Any questions? We'll probably have questions here, but as we kind of work through these, it'll maybe make a little more sense once we get some actual values to this. Okay? So how do we build a confidence interval for the difference between two population means? So I think this will help if I do this. Okay? Just write out some things that we know. When it comes to a one population example, we said the confidence interval looked like this, right? Where this guy right here represented the standard deviation of our sample means, right? That was what we've done in the last exam. Okay? Well, the new thing that I'm interested in is the difference in sample means. So you can almost think about it as before the statistic I was interested in was just one group's mean. Now what I'm interested in is the difference in two group sample means. So like this is my statistic. It's actually like a statistic calculated from two other statistics, right? I find two sample means and then I took the difference. So this is the statistic I'm interested in. Because I know the population mean of each group, and just as a reminder, the standard deviation, the difference in the means, we said was the square root of each group's variance over its sample size. Okay. Well, because I know the population variances of each group, I can still use that standard normal distribution. Right? And now I'll multiply by the standard deviation of the statistic I'm interested in. Before, that was the standard deviation of my sample mean. Now it's going to be the standard deviation of the difference in my sample means. So, you know, I could write this right here, or I could plug this formula in, right? It doesn't matter. We can calculate the intermediate step, or we can just write it all in at one time. Right? And now the process is really identical to what we did before. You'll look up that z value the same exact way. It's just now we have a few more moving parts in that confidence interval equation, right? We've got a few more things to plug in. Okay? Now, when it comes to these two population examples, and the reason why I started to show you this with the one population example, I think calculating this standard deviation of the difference in sample means, like calculating that intermediate step, becomes a lot more helpful now because it just creates fewer like moving parts once we get to actually enter this into our calculator. And you don't have to. I think it makes it a lot easier if we calculate this intermediate step now. Okay. Any questions on any of this? Like I said, everything's still really the same format, right? I'm just taking the sample statistic I found. It's just that now that statistic is the difference between sample means. I'm still looking up that z-score the exact same way. Alpha still has kind of the same interpretation. It's just that now I need to go, this is how many standard deviations away I need to go from that sample I found. Before, my standard deviation of my sample mean was this. Well, now the statistic I'm looking at is the difference in sample means. So I have to use the standard deviation for the difference in sample means. Right? But I'm still, right? Standard deviations, z-score, the statistic I'm interested in. Any other questions on this? I feel like this is a little blurry, so if you can't read something, please let me know. Let's see if I can find the remote. Let's see if this helps. Maybe a little bit. Okay. So, all right, we basically arrived at what I just had written down there, right? Everything else is the same, right? And I kind of mentioning what we've already said. Right? So what are the steps? Well, looks like there's a lot going on here, but it's because it's the same piece of information we needed before, but now we've got two groups. So we need the sample mean from each group, the population variance from each group, and the sample size from each group. We'll still need an alpha, right? We need to know if we're building the 90, 95, 99% confidence interval. Once I have that alpha, I know that I want alpha over 2 on either side of my confidence interval. So I'll find the z-score that would give that to me. And then it's just a matter of plugging things in, right? So I plug in everything here, subtracting that margin of error to get my lower bound, adding that margin of error to get my upper bound. And I also mentioned if you want to, you can add another step in here, which is go ahead and calculate that standard deviation of the difference in your sample means first. So I'll work through it both ways here today. So let's go back to that motivating example and work through this one together. So we've got what? 40 econ majors, 50 theater majors. We've got a sample mean from each group, and we're told what the population variance is. So I'm going to start out, just so I don't get any of these numbers wrong, just writing down what we know. Okay? Now, if it helps, you can write this out as group 1 and group 2. Sometimes it helps just write it out, use a subscript that applies to this example. So I'm going to go the sample size for econ majors was 40. Sample size of theater majors was 50. Sample mean for econ majors was what? 45,000. Sample mean for the theater majors was 33,000. Variance, population variance for each group. And those were what? 9,000. And 6,000. Okay. Now, if we look at this, right away you're like, well, okay, I've got the econ starting salary is quite a bit higher than the theater majors, right? But what could have been true is I just so happened to see, like, even if the econ majors were lower, right? If in fact they did have a true lower population mean, I could have seen a sample mean for my econ majors up here and a sample mean for my theater majors down here, right? And just because my sample difference would be that econ majors make more, the true population difference could be that they in fact do make less. Right? That could be the scenario. So I'm going to build this confidence interval to be able to say, okay, what are the range of possible values for what this difference could be if I'm willing to build this at the 90% level? Because look, we could see these sample means, but look, they're pretty far into the tails. We know that it's not very likely that those are the two sample means we found. Right? So we're going to go ahead and build our confidence interval. So before I kind of jump to just the dot cam, what would our alpha be here at the 95% confidence level? 5%, or in decimal form, 0.05. But we need, we kind of remember, half of alpha on each side. So we'll take 0.05 divided by 2. Right? So 0.025. Go to that standard normal table. Ooh. Oops. So 0.025 is the area we want in the tail. So we start hunting for that. 0.025 right here. Now, you'll notice these are the same values that we were finding before for one population example. So like once we get to this step, this is going to look just like what we were doing before. So you hated hypothesis testing and weren't doing great before. We still have to spend a little more time on it, right? Making sure we know how to find those values, critical values, know how to find the values that we need to build that confidence interval. But it's going to be the exact same way. So 0.025 will be negative 1.96, right? But we said that positive and negative sign is really built into our lower and upper bounds, so we just need the absolute value, or 1.96, right? So we just looked up that z value we needed, which was 1.96. Okay? Now this is where, it's really just a matter of plugging our values in. Once we get to this point, and I gotta write this out, so theater majors, econ majors, right, we've got our z-score. And this is where, I don't know. I personally think it's easier if I just remember, oh yeah, I need the standard deviation for the difference in my sample means here. So I'm going to go ahead and calculate that ahead of time just to make my life a little bit easier. So I'll take the square root of, and if we, so I have it written down somewhere. Here we go. Right? We had that was just the population variance for each group divided by its sample size. So group 1 has a population variance of 9,000, sample size of 40, plus 6,000 was the population variance for group 2, divided by their sample size of 50. I didn't take my calculator out. I didn't, so I can kind of calculate this. So we go, the square root of 9,000 divided by 40 plus 6,000 divided by 50, approximately 18.57. Okay. Well, now we've got everything that we need, right? I've got my two sample means, so that was 45,000 minus 33,000. That's what I'm centering my confidence interval around. I'll then add to get my upper bound, subtract to get my lower bound, using that number of standard deviations away that I want to go, that z-score. And then here, when I've calculated the intermediate value, well, now it's pretty easy because I just have to plug this guy in here. Right? Okay. Any questions on anything I did there? Okay. Now, go ahead, if I were to give you some potential answers here, right away we should know that this confidence interval is centered around what value. So sometimes it helps to do this as well. What was the sample difference that I found? 12,000, right? So I know that my confidence interval should be centered around that value, right? I'm going to go a certain amount to the right to get my upper bound, a certain amount to the left to get my lower bound, right? But I know that it should be centered at 12,000. Okay? So these are some of the principles to kind of remember as we're working through these. So, I don't know. If we go ahead and we plug this into our calculator, where are we at? There we go. We kind of already did the hard work here. Now it's just a matter of kind of getting that entered in. Now, if you didn't want to calculate the intermediate step, you could have plugged it all in, at one time. It just, there's a lot more parentheses and a lot more moving parts. I think it just makes it a little bit more difficult. Now, I chose these variances, and I probably actually didn't have the variances. I probably had the standard deviations because we got a pretty tight kind of window here, right? Which is good. We did have 40 and 50 people from each group, so we had a decent sample size, and we did see a pretty large difference, but I get a pretty tight confidence interval, which is that it's between 11,964 and 12,036, right? So when we start to look at these differences, right, when we look at these confidence intervals, what this is telling me is that with 95% confidence, right, that the true difference is definitely positive, and it's somewhere within this range, okay? So this one's not as interesting once we have because it's a pretty narrow range of values. So we'll go to another one that's maybe a little bit more interesting that we can think about how the interpretation of these confidence intervals could be really useful. But here with 95% confidence, I can say that econ majors are making more money than theater majors. In fact, I can say with 95% confidence, they're making, this amount more, somewhere in this range, right? Okay. So let's look at a different example. And my mouse is going crazy. Okay, so here's one that's maybe a little bit more, could be a little more interesting. So I've got two time periods here, or no, I've got two states here, sorry, same time period. 1982 to 2005, which is basically 24 years of data for each state. Right? So this one's kind of unique in that I've got the same number of years for each state, so I've actually got the same sample size, 24 years from Indiana, 24 years from Ohio. I find that the annual kind of mean, the robbery rate in Indiana was 109 across these 24 years per 100,000 people, and then 163 in Ohio. So I've got each state's population variance as well. So I'm going to build a 95% confidence interval for the difference between Indiana and Ohio. So here's where we have to be a little bit careful when we're looking at these differences between, difference between two populations in terms of how is it set up. So here we're looking at Indiana minus Ohio. So if we think about, just to kind of, before we get too far into it, the sample mean I found from Indiana was 109. Sample mean from Ohio was what, 163. Indiana's sample size was 24, and here we have this unique example where the sample size from each group was the same. And then finally, what are our population variances? 175 for Indiana, 497 for Ohio. I'm just writing down what I was given there, and I'll blow this up in a second if you're trying to kind of go on. Okay, so I with a 95% confidence interval. So hopefully, if you were paying attention to the last example, what should the z-score I need be? Yeah, the exact same thing. I want the same percent confidence interval. Alpha is still going to be 0.05. Alpha over 2 is still going to be 0.025. When I look 0.025 up in the table, I'm always going to find the same values in that standard normal distribution. So we kind of can cheat a little bit here. And we know the z-score we need is going to be 1.96. Okay? All right, so from here, if I just think about, okay, the difference that I wanted was Indiana minus Ohio, okay? So what was the sample difference that I found? Well, 109 minus 160, oh, I forgot the 163. So I get what, negative 54? So I know that my confidence interval should be centered around whatever that sample difference I found was. So if I looked at those answers on there, I can rule out D right away, right? Because my sample difference isn't even in that range. Right? If I look at the other ones, it looks like negative 54 is kind of, yeah, I think it's in the middle of all of these. So I can't really rule any of the other ones out. So from there, it's a matter of kind of getting things plugged into that confidence interval equation that we had here. Right? So I've already got that sample difference. I could calculate the intermediate step, which is find the standard deviation for the difference between the sample means for Indiana and Ohio. And that's just D. square root of each group's population variance divided by its sample size. So 175 over 24 there. And actually, if it helps, get this all on one line. There we go. And then, and I wrote IN here. This was Ohio on the other side. And then Ohio's population variance divided by Ohio's sample size. Okay. So I've calculated this intermediate value, which is this guy here. I have my z-score, and I already have that difference. Now it's just a matter of plugging everything in. Okay. So if I do this, just to kind of help you out if you're kind of working along these intermediate steps, approximately 5.29, okay? So I'll take that sample mean difference, add to get my upper bound, subtract to get my lower bound, plug in that z value, and then the final thing is, well, I calculated this intermediate step, so multiply by the standard deviation of the difference in those, which was 5.29. Okay. Now I'm kind of switching back and forth to the formula so you can see it. So any questions on anything I did there? Why did I plug in a certain value there? And like I said, you can do it all on one line. So I think in the slides, we'll get a taste of that. So we identified all the pieces of information we were given. We found that z-score. We actually cheated and used it from the previous problem. And if you wanted to plug everything in all on one line, you can do that and go ahead and enter that in your calculator. I just find it easier to break it down into steps. Okay? So we've got a range with 95% confidence. I could say that the true difference in robbery rates between Indiana and Ohio is -64 and -43. Or said differently, right? Indiana, with 95% confidence, I could say, has somewhere between 64 and 43 fewer crimes kind of per person. It was per 100,000 people, but per person there. It's another way we can think about it. So the reason why this is interesting is because if I have a confidence interval and the only values here are negative, I can with 95% confidence say Indiana has lower robbery rates than Ohio, right? Not to pick on Ohio too much, but right, that's with 95% confidence I could say that. Now, what if I had went through all of this? In fact, I want to waste a lot of paper, so I'm just going to write it down here. What if what if I had went through all of this and I had found, I don't know, -100 to 20 or something like that? Well, if this is my confidence interval for the difference between Indiana and Ohio, right? Well, I'm thinking about the true population difference is somewhere in this range. The issue is the true difference could be negative, which would mean that Indiana has lower rates than Ohio. But the true difference could also be positive values, which would mean that Ohio has fewer crimes than Indiana. One of the true values, in fact, could be 0, right? 0 is in that range. So at the 95% confidence level, I can't actually say, right, one of the true values could be 0, that these two groups, that their population mean is exactly the same based off of the sample data that I found. So anytime we have a confidence interval, when we're looking at these two population examples, if it includes 0, we really can't say a whole lot, right? Because we can't say, could be that, group 1 had a higher population mean, could be that it had a lower population mean, or it could be that both groups had the exact same. Now, when we had a scenario like it's only between -64 and -43, well, now I can say with 95% confidence that that true difference is going to be a negative value, right? That Indiana's was actually lower than Ohio. So this is kind of the power of doing this two population stuff. Before we were like looking at, do the confidence intervals overlap? Well, that's essentially what we were doing, right? It's not as theoretically correct, because when we were doing that, we weren't actually taking into consideration that there may be different sample sizes between the two groups. But I wanted to introduce that idea because it sets us up for now thinking about there's actually a better way to see whether or not one group has a higher or lower mean. Okay. Any questions on that idea? Okay. All right. Where are we at today? We got 13 minutes, huh? We'll at least introduce this idea of hypothesis testing, okay? So if we can build a confidence interval for the difference between these two population means, right, like where that true difference could be, we can also do hypothesis testing, right? And we can do it for means or proportions, but today we'll focus on means, right? So what we're going to do is we're going to call the difference between the two means just kind of capital D, right? So we're going to then assume that the true difference is some value kind of capital D subscript 0. This is going to be very similar to what we're doing before. Before we just wanted to know where one mean was, and we had an assumed true mean. Now we're going to have, we're wondering about what the true difference is, and we're going to have an assumed true difference. Okay? Now, I say often here, for the sake of what we're going to be doing in this class, I'm always going to keep this assumed true difference 0. Okay? And we'll see why that's usually the case. And we can test against other values, and I'll probably show you an example like that on Friday. But we don't have to use 0 here. It's just that for what we're going to be doing, any problem I'm going to ask you, we're always going to be using 0 here as the assumed true difference. Okay? So just like before, we have 3 types of tests: left, right, two-tailed test. Is the true difference greater than a certain assumed value? Is it less than an assumed true value? Or is it not equal to, right? We still determine what kind of test it is based off the alternative hypothesis. So we've got 2 one-sided tests and then that 1 two-tailed test. Everything's going to work exactly the same. Okay? Finding the p-value, finding critical values, everything's going to be exactly the same with the exception of 1 step. So can anybody guess maybe what that step would be? So if we think about how we do hypothesis testing, I guess technically identifying the null and alternative will be a little bit different, right? I mean, if we just replace capital D here with mu, though, everything's going to look exactly the same to what we were doing before. What about finding critical values? Well, I still got left, right, and two-tailed tests. So think about the area I want in the tail, and then I go to the standard normal distribution. I can find those cutoff values. That's not going to be any different. But what if I want to do the p-value approach? Okay, well, if I'm doing the p-value approach, I need my test statistic. Now remember, what did the test statistic represent? It's still a z-value, so it's the number of standard deviations away from the assumed true mean. Well, now it's going to be the number of standard deviations away from the assumed true difference. Well, if I'm thinking about standard deviations, I now know that my standard deviation looks a little bit different. So the step, it's really going to be different is when we calculate that test statistic. Okay? So, determine the null and alternative, not a lot different there. We're going to need an alpha level to find these critical values or even to test our p-value against. So we can find the critical values the same way. It's just now our test statistic. Oh, I thought I had it on this slide. Oh, I guess I'll write it out for you. So our test statistic now is going to look a little bit different, okay? Before, when we wanted the test statistic for one population example, we took the sample mean, subtract the assumed true mean, and then we divided by square root of the population variance over our sample size, where this denominator represented the standard deviation of our sample mean, right? We're going to be doing the exact same thing. It's just now our test statistic or our z statistic, we're not looking at the sample mean anymore. We're looking at the difference in our sample means. We're then going to subtract not the assumed true mean. You can kind of think about this as, right? This is kind of like the sample difference we found. Right? We're then going to subtract not the assumed true mean, but the assumed true difference. Now, I said usually, for our examples, like on the exams, I'm going to keep this at 0. So this almost like kind of goes away, right? But it is still technically there if I wanted to test against anything other than 0. I'll then divide by not the standard deviation of my sample mean, but the standard deviation of my sample difference, right? So if I want the standard deviation of the difference in those sample means, well, just like the confidence interval, I know that that's equal to each group's population variance divided by its sample size. Right? So my test statistic does become a little bit more, there's more moving parts here, but it's still going to represent the same thing to me. How far away was the sample difference I found from that assumed true difference? Not just how far away, but how many standard deviations away was it from that assumed true difference? So the idea of what we're doing is still the same. It's just instead of the statistic of the mean, we've now got this statistic of the difference in means. Okay. So we've got our test statistic equation now. Once I have that test statistic, it looks identical to what we were doing before. I looked that z-value up in the table, find the area to the left for a left-tailed test, area to the right for a right-tailed test, area in the tail, and then multiply it by 2 for a two-tailed test. Once I have the p-value, I compare it to alpha. All those steps are exactly the same. So really the only difference there was kind of step 4 was calculating that test statistic. We had a slightly different equation. Okay? And I'll leave this kind of up here. Any questions on this? If you're still writing it down, I can see some of you, so I'll blow it up a little bit more for you. All right. So, we do the p-value. Oops. P-value approach, everything's exactly the same. I mean, these are the exact same slides I've shown you before. Critical values, going to keep finding the same critical values we were before as well. Nothing really changes here. The only real difference was this test statistic equation, right? But it follows the same format. Whoops. We take that statistic that we were interested in, the difference, sample difference, subtract the assumed true difference, divide by the standard deviation of that statistic. Okay? So yeah, you can write that as kind of, I guess, d hat if you really want to. That kind of helps make a little bit more sense. All right, so we'll start out with this example, and let's kind of see that, it is the same procedure, but identifying the null and alternative hypothesis is a little bit trickier with these two population examples, because usually the way that we think about it is a little bit different. So let's say we have two time periods, 1990 to 2011 and 1958 to 1989. Right? From each one of those time periods, right, 22 and 32 years, so that will be our sample size. Over these 22 years, we find a sample mean of tropical storms in the Atlantic of 15.5. And over this older time frame, we find a sample mean of number of tropical storms to be 9.7. We somehow have the population variance. Once again, these aren't the most realistic application problems, but we're going to start here and then move to if we only have sample variances eventually. So if I've got the difference between these two and I want to test for whether or not tropical storms have increased. Well, this gets a little bit trickier to identify the null and alternative than with a one population, because with a one population, I could say, is a tropical storm number greater than this amount, or is it less than, or is it different from? Well, now we're going to be comparing these two, and so the way we would say it in English is, have they increased? Well, what is that really saying, right? So if I think about tropical storms, anytime I have, or this tropical storm example, anytime I'm looking at like the difference in years, I'm thinking about, is that mean for the newer time period minus that mean for the, oh shoot, hold on. So here is the kind of newer time period, and I believe the older time period ended in 1989. Right? So these are like the old years, here is our newer year kind of population mean. If tropical storms have increased, what we're saying is, we want to see whether or not the mean in the newer years is greater than the mean in the older years. Well, if that's what we want to test for, you can kind of think about that's your alternative hypothesis. Now, the problem is the way that we write this null alternative hypothesis, the statistic we're actually interested in is going to be the difference in those time periods, right? So how can I get my alternative hypothesis to look, have the actual difference there? Well, if I subtract this from both sides, what I actually end up with something like this, where this is really my assumed true difference. Right? I'm assuming that it's, or sorry, here's my alternative. So my null would be what? The exact same thing, but the complement so that it's less than or equal to 0. Right? So here's what I want to test for. I assume the opposite is true. So my assumed true difference value is that 0, and then I really have kind of the true population difference now as the statistic that I'm interested in. But the problem is when these word problems and the way that we say things, we usually say it like, have they increased, right? Well, if they've increased, then that difference should be positive, right? The new average should be higher than the old average, which is really what we ended up with here. Now, you don't have to like write this out and then subtract it from both sides to get the difference. I'm just trying to make that connection for you. If you read this and think about, oh yeah, if tropical storms have increased, then that means that difference would have to be positive. And if it's decreased, I would think, well, it has to be negative, right? The newer mean would have to be smaller than the old mean. But you can think about it this way as well if that kind of helps. Okay. So I know that I don't have these written in the traditional order because I didn't give myself enough room up here. But here's my alternative. Here's my null. So I look at my alternative hypothesis. I have a greater than sign. So I'm going to have what type of tailed test? A greater than or right-tailed test. Okay. And we'll get some more practice kind of identifying these null and alternative hypothesis with these two population examples. Like I said, it is a little bit trickier, but hopefully as we work through a few more examples, we'll become more and more comfortable with this. Okay. Any questions on any of this? All right, so what we're going to do Friday is kind of continue with a couple more examples here. We might start proportions, but the way that I'm going to do this is, I'm going to start out, we're going to be going through these examples where we have two population means and we know the population variances. So we've done confidence intervals. We'll finish up hypothesis testing with it in another example on Friday. I'll then show you how we would do it in Excel, all right? So I didn't spend a lot of time with hypothesis testing in Excel for one population. So I spend a lot more time for these two population examples. And there's a reason why. So I'll work through some more Excel stuff on Friday, and then we'll move to two population proportions. I'll show you how to do confidence intervals, hypothesis testing, and how to do it in Excel. Then we're going to go to our final one, which is we've got sample means, but we only have sample variances. How do we do confidence intervals, hypothesis testing? I'll show that to you in Excel. Okay. So I've got the Excel files up there already on Canvas, but it's going to take us a while to kind of build them because we're kind of going to be going like piece by piece. That's the way I just described it. Okay. All right. So look for those kind of exams to be graded here. Like I said, hopefully I'll get through a good majority of them by Friday, but it might not be until Monday that everyone's is graded and I have more information on kind of where the average was. Okay. All right. Enjoy the weather this afternoon. I will see you on Friday.